Hello everyone, welcome to Gate Academy. How are you all? Good morning. Good morning all. Okay, please tell me audio, video are clear or not. Thank you Raja. Thank you very much. Please continue my classes, okay? You will get know everything in electrical machine. Okay, thank you. Okay, listen. So let's get discuss. In previous session, we had discussed about operating principle and working of the transformers. Okay, what is the operating principle of the transformer and how does EMF induced in the primary winding as well as secondary winding of the transformers. Okay, transformer operates on the principle of Faraday's laws of electromagnetic induction. It states that an EMF induced in a coil or winding is directly proportional to rate of change of flux linkage. And after our discussion, we had concluded that EMF induced in the transformer is a statically induced EMF and EMF induced in the primary winding is self-induced EMF and EMF induced in the secondary winding is mutual induced EMF. Okay, this part we have discussed in the previous class. Okay, so today in this session I would like to discuss about the another topic of transformer, that is a EMF equation of the transformers here. So previously we had discussed about how does EMF induce in the transformer winding. So in this session, what is the EMF equation of the primary winding and what is the equation of the EMF equation of the secondary winding of transformer. Okay, this part we are going to be discuss, and after that we will discuss about and what are the possible questions from the EMF equation of the transformer. So that means, so derivation part, everybody knows the derivation, how do we derive the EMF equation of transformer. But what are the possible question behind the derivation? So that is a very important for competitive exams. Am I right? So now we will discuss one by one. Yes, Das Gupta, yes, every day at 11 a.m. you have a class, okay, in the channel. Okay. So we know whenever transformer excited with the AC supply, what will happen? So let assume here transformer winding is excited with the AC supply, that is a single phase the AC supply. Then what will happen? So this single phase AC supply I represented with the V1. Okay, V1 is a single phase AC supply. So when transformer is excited with the AC supply, time varying nature of the current passes through the winding. Okay, this current is known as magnetizing current. What is the mean by magnetizing current? Okay, magnetizing current क्या होता है? The current required from the source. Okay, कितना current है to produce the flux? Okay, how much amount of the current required from the source to create the flux is known as a magnetizing component of the current. So now here this is a, let us assume N1 is a number of turns in the primary winding of transformer, whereas N2 is a number of turns in the secondary winding of transformer. So now this current is a magnetizing current. So assume as yesterday I have discussed that. So suppose current is a entering position. So this is a current entering like this. So what will happen? According to the right hand thumb rule, okay, if thumb indicates the current, if the orientation of the fingers indicates current direction, then thumb indicates flux direction. So that flux is this flux is a phi 1. So flux produced in the primary winding, okay, this flux produced in the primary winding, which also links in the secondary winding, okay, through transformer core, okay, like this. So now whatever flux produced, okay, due to this flux here, EMF induces in the primary winding as well as EMF induces in the secondary winding of transformer. So this is the theory behind this, okay. I repeat once again, listen. Whenever transformer is excited with the AC supply, time varying nature of the current passes through the winding. So due to which flux will be created in the primary winding. Whatever flux produced in the primary winding also links in the secondary winding through transformer core. According to Faraday's laws of electromagnetic induction, EMF induces in the primary winding as well as EMF induces in the secondary winding of transformers. Okay. So now our question is, it's the EMF equation of the transformers. Okay. So how do we get that EMF equation of the transformer? The see here all of you, okay. So let the I nu is what we conclude. So let I nu is the magnetizing current of transformers, okay, magnetizing current of transformer, and V1 is let V1 is a supply voltage of transformer or applied voltage of the transformer. So transformer is a pure inductive nature, okay, this transformer is a pure inductive nature. So that means it acts as like a pure inductor. So now this one is the transformer, we know the transformer, okay, is the pure inductive nature, okay, is the inductive nature. So therefore what will happen? So this inductive nature, so this is the pure inductive nature, so that, so here is the magnetizing current, the lags the applied voltage, so by 90 degrees here, okay, this point. So it is a very important, the transformer is a pure inductive nature, okay, so that the magnetizing current lags the applied voltage by 90 degrees, okay. So if I take, okay, here is so if the V1 is equal to the Vm sin omega t, okay, so then what will happen? I nu will become, so that is I maximum, okay, sin omega t minus pi by 2, okay, this is equation 1, okay. So if I take V1 is equal to V maximum sin omega t, then I nu is equal to Im sin omega t minus pi by 2. Suppose other way also we can take, okay, per our convenience. Suppose if I take V1 is equal to, okay, V maximum the sin omega t plus pi by 2, okay, then so what will happen? I nu will become, so that is I maximum, okay, sin omega t, okay. So both are correct, okay. Here if I take suppose, so V1 is a Vm sin omega t, then magnetizing current will become I maximum sin omega t minus pi by 2. And what about other equation? If I take V1 is equal to Vm sin omega t plus pi by 2, then a magnetizing current I nu is equal to Im sin omega t. So let us assume, okay, you can take any one, this is the equation 1, okay. So in general we have considered this one, okay, I nu is equal to Im sin omega t. So that means the applied voltage leads the magnetizing current by the 90 degrees, okay, clear. So now coming to the here, so after the flux, the always I have mentioned that, so what will happen? The primary MMF, okay, the primary MMF of transformer. So primary MMF means number of turns multiplied by magnetizing current. So now after that primary flux of the transformer, so this primary flux also called mutual flux of the transformer. So that is equal to N1 I nu by the reluctancy of the core, okay. So this is equal to n1. I knew we can write Im the sine omega t and divided by reluctancy of the core. Okay, simplify here. Okay, this is equal to the n1 Im by reluctancy of the core. So multiplied by okay sine omega t. So this equation okay also we can write. So it is equal to phi maximum the sine omega t. So where phi maximum is equal to, what does it mean by phi maximum? N1 I nu by the reluctancy of the core. Okay, clear point? So now this is the N1 I nu by reluctancy of the core. Okay, good morning all. Okay, next see here. So this is the primary flux pi 1, that is a pi maximum is equal to I nu by reluctancy of the core. So now first one let us find out. So this flux is equal to, let us assume, so it is the equation 2 here. So from 1 and 2 equations, what we conclude here? So from the 1 and 2 equations, okay, we get, so that is the magnetizing current and flux, primary flux are in phase with each other. Okay, in phase, so with each other here. So this point is a one of the point, the one is a very important to draw the vector diagram of transformers. Okay, so from 1 and 2 equations, what we conclude here? So that is the magnetizing current and flux of the transformers are the in phase with each other. Okay, so next one, let us find out the induced EMF in the primary winding. So induced EMF in primary winding of transformer. So EMF or induced EMF the in primary winding. What is the formula here? So according to the Faraday's laws, okay, V1 is equal to, so that is a V1 minus N1, okay, d phi 1 by the dt. So this is the V1 is equal to minus N1, the differentiation of the flux with respect to the time. So differentiation of the flux with respect to time. So now simplify this. Okay, V1 is equal to minus N1 phi maximum omega. So that is a cos omega t. So this cos function we can write in the sign. Okay, this is equal to minus N1 okay phi maximum omega. So in terms of the sign, okay, this is equal to, so it is a phi by 2 minus omega t. So when minus is a common, then we can write N1 the phi maximum omega sin, okay, phi by, this is the omega t minus phi by 2. So this is the assume, okay, here is a, so V1 okay is equal to, this value we can write the V1 maximum the sin omega t minus pi by 2. So let us assume this is the equation 3. So from this here also we have a, so this EMF is known as the instantaneous okay induced EMF the in primary winding of transformers. Okay, instantaneous induced EMF in primary winding of transformer. So this where E1 maximum is equal to, okay, this E1 maximum, so that is equal to N1 phi maximum omega. So now here also we have a one conclusion. See here, so that is a first equation 2. Okay, what is the equation 2 here? Phi maximum sin omega t. And what about the equation 3? So that is the E1 is equal to E maximum sin omega t minus pi by 2. So that means from 2 and 3 equation, what we conclude here? The EMF induces in the primary winding lags the flux by 90 degrees here. So therefore here, so from 2 and, okay, this is a, so we have a one conclusion. See here all of you. So from, okay, 2 and the 3 equations, okay, we get, so another conclusion here. So what is the conclusions? Okay, E1 lags the phi 1 by, okay, by 90 degrees. Okay, 90 degrees here. So E1 lags the phi 1 by 90 degrees. Clear? So that means initially, okay, here is a, suppose if we take there, so that is a initially flux produce, okay, at some instant, and after 90 degrees time delay, suppose after 90 degrees time delay, the EMF induces in the primary one. So this one is the phi 1 and this is the V1 here. So how much displacement here? Okay, that is a pi by 2. Okay, this one is a the phi by 2 values here. So now EMF induces in the primary winding, the lags the flux by 90 degrees. So this is also one more conclusions. So now I have mentioned that. So this is the conclusion, okay, 2, okay, and this one is the conclusion 1, okay, like. So all are very important to draw the vector diagram of transformers, okay. So next coming to the here, so in this case, what about this value, okay, sometimes, so we have a question, maximum the value of induced EMF, okay, induced EMF in primary winding of transformer. So what is the maximum value of induced EMF in the primary winding of transformer? So that is a E1 maximum is equal to N1 phi maximum omega. But all AC voltages are measured in the RMS value but not in the maximum value. So therefore we can write, so that is a RMS value of, okay, induced EMF, okay, this induced EMF in primary winding of transformer. So that is represented, so that is a E1 RMS. So it is represented with capital letters E1. So now this one is a E1 RMS. So how do we get RMS value? The E1 maximum divided by the root 2. So that is the maximum. And what is the maximum value? N1 phi maximum omega divided by the root 2 here. So this omega we can write, okay, it is a N1 phi maximum, omega is a 2 phi f, okay, this is the 2 phi f divided by root 2. So now simplify this, okay, this will become, so here is a 4.44, the phi maximum fn1, okay, fn1. So therefore we can write, so RMS value of induced EMF, okay, E1 is equal to, so 4.44 phi maximum fn1. So this is a EMF equation of the transformer, okay, this EMF equation of transformer in primary winding. All of it clear now? So is there any doubt? We have two conclusions. One is a flux and magnetizing current are in phase with each other, and second one is a EMF induced in the primary winding lags the flux by 90 degrees, okay. Is that clear? Any more doubt? समझ आया आपको? कुछ डाउट्स है क्या आपके पास? कुछ सवाल है तो आप पूछ सकते थे, कोई दिक्कत नहीं. समझ गए? वेरी गुड. समझना चाहिए. I am teaching you very in detail, okay. Even though if you have a doubt, you can ask. Okay, no need to shy to ask your question. I am always welcome your question. कुछ भी क्वेश्चन, आपको कुछ भी सवाल है एप्स के बारे में आप पूछ सकते थे. मैं बता दूंगा आपको अच्छे सा, हिंदी और इंग्लिश में दोनों में बता दूंगा. ओके. Taksha Patel, transformer behavior when pulsating DC supply given. Okay, pulsating DC supply here, when it is a suppose when transformer is excited with a DC supply, okay, it is a pulsating or DC, what will happen? The EMF induces, okay, EMF induces in the primary winding will become 0. Okay, so when EMF is equal to 0, it behaves like a short circuit. So because of this short circuit, very high amount of the current passes to the primary winding, and which can damage the primary winding of transformers. Okay, so now let us discuss another one. So that is a EMF induces in the secondary winding. So EMF induced in secondary winding of transformer. So what is the formula? Okay, EMF induced in the secondary winding of transformer, according to the Faraday's laws of electromagnetic induction, the E2 is equal to minus N2 d phi by dt. So which type of this EMF? Okay, it is a mutual induced EMF. So what is the meaning of mutual induced EMF? Okay, yesterday we have discussed that point. EMF induced in the coil or winding due to relative motion between relative time variation between the magnetic field and set of conduct, that is a statical induced. So this statical induced EMF are two types. The ek is one is a self induced EMF and second one is mutual induced EMF. So mutual induced EMF means EMF induces in a coil or winding due to current passes through another coil. Okay, suppose दो कॉइल है, तो इसमें एक करंट फ्लो होता है और इसमें दूसरा है ना ओपन है. So here EMF induced in the open circuit or loaded circuit. So this EMF, because of the current flows in the other winding which is magnetically coupled through the same flux, that EMF is known as mutual induced EMF. So now E2 is equal to minus N2 d phi 1 by dt. So this is equal to minus N2 differentiation of the flux. So phi maximum, the sin omega t. Okay, right? So now this one you can write, okay, E2 is equal to, so minus, okay, N2 phi maximum omega, the cos omega t. So this E2 is a, okay, here, so minus N2 phi maximum omega, that is a sin the omega t minus pi by 2. So sin omega t minus pi by 2. So now simplify this, the E2 is equal to phi maximum omega, the sin, okay, pi by 2 minus, okay, initially I have written wrong. So see here, okay, that's correct. Directly I have written E2 is equal to N2 pi maximum omega sin omega t minus pi by 2. So this equation we can write, the E2 is equal to, okay, E2 maximum, the sin, okay, omega t minus pi by 2 values. So let us assume equation 4 here. So coming to the, in this case also we have some conclusions. So what is the conclusions here? So from the conclusion number, okay, 3, okay, like, so what is the conclusion? See, the E1, okay, this is the, okay, E2 also lags the phi 1 by 90 degrees, okay, 90 degrees here. And second one, E1 and the E2 are, okay, E1 and E2 are the in phase with each other, okay, E1 and E2 are the in phase with each other. Okay, this is the two conclusions. That means suppose we have a flux, okay, like this. So this is the flux produced in the primary winding pi 1. So now what about induced EMF? Okay, induced EMF. So that is a, this is the induced EMF E1. Okay, and what about the E2? Okay, E2 also magnitude may be different but in phase. Okay, this one is a, the in phase with each other. Okay, so this type of, okay, it is nothing but the E2 values. So EMF induced in the primary winding, so lags the flux by, okay, the 90 degrees, and E2 also lags the flux by 90 degrees, and E1 also lags the flux by 90 degrees here. So now this is the conclusion number 3. Okay, this is also very useful. So to draw the vector diagram of transformer. So from this equation, okay, here, so maximum value of induced EMF, okay, a value of induced EMF. So that is equal to E2 maximum. So what is the value of the E2 maximum? So that is a N2, okay, pi maximum omega. So this one is a E2 pi maximum omega. So now find out RMS value. The RMS value of, okay, induced EMF, the in secondary winding. Okay, this is equal to, so here E2 RMS, okay, is represented with the E2. So it means that, okay, that E2 is equal to the N2 phi maximum omega divided by root 2. So where omega we can write, okay, that is a 2 phi f. So by simplification here we will get the E2 is equal to 4.44, the phi maximum f, the N2 1. So this is the EMF equation of the transformer in the secondary windings. Okay. It is also same. EMF induced in the transformer. Okay, is that clear, everyone? E2 is equal to 4.44 phi maximum f N2. Phi maximum is a maximum value of the flux. F is a frequency. N2 is a number of the turns in the secondary winding, where F in the sense the supply frequency, okay, where N2 is a number of the turns in secondary winding. Okay, so these are the two EMF equation of the transformers. All of it clear? So now we have a question. So this, listen. Okay, so listen here. So what are the possible questions from the EMF equation of the transformer? Observations in the sense just like possible questions in the competitive exams. Okay, what are the possible questions from the EMF equation? Everybody knows how do we derive the EMF equation. Even in the textbook also there, how do we derive, different methods are there. But what are the possible questions from this EMF equation of the transformer? So we know this EMF induced in the primary winding, okay, E1 is equal to 4.44 phi maximum f N1. Similarly, EMF induced in the secondary winding, okay, E2 is equal to 4.44 phi maximum N2, okay, number of the turns. So what are the possible questions from the EMF equation of the transformer? So first possibility question here, okay, one is a, so sometimes we have a question, the EMF equation of the transformer, okay, this EMF equation of the transformer in terms of, okay, this is the, in terms of the flux density, okay, B maximum, flux density and net cross sectional area of transformer core. Okay, this is the one of the question. So how do we get EMF equation of the transformer in terms of the flux density and net cross sectional area of the transformer core? So where B maximum, let us assume C. So in this case, okay, let B maximum in the sense the maximum flux density of, okay, flux the density of transformer core, okay, this one. And what about AN? So it is the net cross sectional, okay, this net cross sectional area of the transformer core. Okay, this is the two parameters. Okay, maximum flux density of the transformer core and net cross sectional area of the transformer core. So how do we get this EMF equation in terms of the maximum flux density and net cross sectional area? So we know that, okay, we know that is the maximum flux density, okay, B maximum is equal to the pi maximum, okay, divided by the net cross sectional area. So from here, okay, this is the phi maximum is equal to B maximum AN, okay, this one. So now substitute this equation, okay, substitute, so this equation in EMF equation of the transformer. So there is a flux pi maximum here in both cases. So by substituting, okay, this by substituting the pi maximum, okay, this by substituting above equation, okay, this above the equation in the EMF equation of transformer, then what will happen? EMF equation of the transformer. So we get, okay, this is by substituting this equation in the EMF equation of the transformer. So therefore here E1 is equal to 4.44, okay, B maximum AN F N1. Similarly, the E2 is equal to 44 B maximum AN F N2. Okay, so now the question formation here, okay, so question कैसे बनता है A equation से? So suppose sometimes, okay, B maximum and frequency number of turns induced EMF are given and asking about the net cross sectional area, and some question, okay, net cross sectional frequency number of turns induced EMF are given, and they will ask the question about the flux density of the transformer core. So these are the two possibility of the question from this equation. Okay, is that clear, everyone? So now one more possibility of the question, okay, second one. So that is a EMF for turns ratio of transformer. So what is the EMF for turns ratio of the transformers? Okay, and what is the relation between the primary winding and, okay, EMF per turns ratio of transformers? So from above equations, okay, see, so from above observations, okay, above observations, so we get, so that is a E1 is equal to, what is the mean by E1? So that is a 4.44 B maximum AN F N1, right? So this equation you can write, okay, it is a E1 divided by N1. So that equal to, okay, E1 divided by N1 is equal to the 4.44, okay, B maximum AN, okay, F, okay, this is the EM. And similarly E2 also, okay, this E2 is equal to 4.44, okay, B maximum AN F N2. So from here, okay, we get the E2 by N2 is equal to 4.44 B maximum AN F. All of it clear? So now what we conclude here, E1 by N1, therefore E1 by N1 is equal to the E2 by N2, so that equal to 4.44 B maximum AN F. Okay, this is the EMF per turns ratio in the primary winding. EMF per turns ratio in primary winding equal to EMF per turns ratio in secondary winding of transformer. So therefore what we conclude here, so in transformer, okay, in the transformer, the here, okay, in transformer, so here is a EMF per turns ratio, EMF per turns ratio is constant, okay, is constant from primary to, okay, this is the from primary to the secondary side, okay, primary to the second. So that means EMF per turns ratio in the primary winding equal to EMF per turns ratio in the secondary winding of transformers. Okay. So now this is also one more possibility of the question. Sometimes we have a question that find out, okay, EMF per turns ratio of transformers. Okay. Now next another possibility of the question from the EMF equation. Okay, let us third possibility of the question is the transformation ratio. Okay, transformation ratio of the transformer. So it is denoted by K. Okay, transformation ratio of the transformer. So in general, the transformation ratio is denoted by the K. So how do we get transformation ratio? So this is also we can derive from the EMF equation of the transformer. So from the above observation, okay, from the above observations, okay, so what we conclude here, E1 by N1 is equal to, so E2 by the N2. So this is by rearranging these terms, okay, that is so N2 by N1, so it is equal to the E2 by E1, okay, this is represented with a K. So where K is nothing but the transformation, the ratio of transformation ratio of transformers. Okay. Now sometimes we have a question about, so that is a turns ratio. What is the mean by turns ratio? So turns ratio in the sense, okay, see the turns ratio, okay, note, so here is it. So what is the turns ratio? Okay, this turns ratio mentioned or represented with the A. It is always the reciprocal of the transformation ratio. Okay. So now in exam point, okay, there is a question. So example point, suppose we have a question like a single phase, okay, 50 hertz, the 400 upon 200 volts transformers. Okay, the 200 volts, the transformers are given. So this is the voltage, the rating. I already mentioned that always voltage rating mentioned on the nameplate details. Okay, this is the nameplate, the details of the transformers. So voltage rating mentioned on the nameplate details, always the induced EMF in the primary winding, the divided by the induced EMF in the secondary winding, but not applied voltage and secondary terminal voltage. So voltage rating mentioned on the nameplate details is always primary induced EMF to secondary induced EMF, but not applied voltage and secondary terminal voltage. Okay, so that how do we find out the transformation ratio? So that is equal to E2 by E1. So this is a 200 divided by the 400, okay, is equal to 0.5. So therefore if you want to find out our turns ratio, okay, this A is equal to turns ratio 1 by K, so 1 by 0.5, it is equal to the 2. Okay, this one is the turns ratio and transformation ratio. You can use any one. So either transformation ratio or turns ratio of transformers. Okay, so these are some questions. Okay, how do we find out? The 3 or 4 questions are there here. One is the transformation ratio and second one is the EMF per turns ratio of the transformer. So what is the conclusion? In transformer, EMF per turns ratio is constant from the primary winding to secondary winding. And another one, this is a EMF equation of the transformer in terms of the flux density and net cross sectional area of the transformer core. So this is also we can derive from the EMF equations of the transformers. Okay. So next another observation. Okay, fourth observation, see. So fourth observation or fourth possibility of the question, that is relation between size of the transformer and frequency of the transformer. साइज ऑफ क्या रिलेशन है, साइज और फ्रीक्वेंसी का, द फ्रीक्वेंसी ऑफ ट्रांसफॉर्मर का रिलेशन क्या है. सो दैट इज द रिलेशन बिटवीन द साइज एंड साइज ऑफ द ट्रांसफॉर्मर एंड फ्रीक्वेंसी ऑफ द ट्रांसफॉर्मर. एनीवन कैन आंसर दिस? व्हाट इज द रिलेशन बिटवीन? Sajal asking why you are using kVA rating now, not in kilowatts. Okay. Sajal, I have discussed this question in my first class. Okay. मैं ए क्वेश्चन का जवाब फर्स्ट क्लास में डिस्कस किया था. You just go there and watch that video. You will get everything. I have discussed that point in the first class only. Yes, definitely I will solve some numericals after this possible question. We have a many question to solve, so everything I will solve here in this session only. Okay, all possible observations, that means possible questions, then I will solve some problems based on this topic. Okay, now okay, ये बताओ पहले आप रिलेशन क्या है. रिलेशन बिटवीन द साइज ऑफ द ट्रांसफॉर्मर एंड फ्रीक्वेंसी ऑफ द ट्रांसफॉर्मर, दोनों में रिलेशन क्या है, क्या रिलेशन है साइज का और फ्रीक्वेंसी ऑफ द ट्रांसफॉर्मर का. ट्राई योरसेल्फ. रिलेशन क्या है साइज ऑफ द ट्रांसफॉर्मर का और फ्रीक्वेंसी ऑफ द ट्रांसफॉर्मर का. ओके, आंसर इट. इफ इट मे बी मिस्टेक, नो इशू. गलत भी हो सकते हैं कभी कभी, कोई दिक्कत नहीं. मैं बता दूंगा बाद में आप क्यों गलत किया था. आई विल मेक इट करेक्ट. Size inversely proportional to the frequency. Okay, param given size inversely proportional to the frequency. Okay, next, any other? No problem, we can do whatever, we can write whatever you want. Think about this question. What is the relation between size and frequency of the transformer? Okay, see, if not get it, so relation between the size of the transformer and frequency of the transformer. Okay, so this relation also can be obtained by using the EMF equation of the transformers. Okay, how do we obtain this EMF equation of the transformer? We know, so we know that this is we know EMF per turns ratio. Okay, that is a E1 by N1 is equal to E2 by N2, right? Okay, E2 by N2. So that is equal to 4.44 B maximum ANF. Okay, ANF here. So this E1 by N1 is equal to E2 by N2. The 4.44 B maximum ANF values here. So now here is this B maximum is some finite value. So it depends on the type of the material. Okay, this is the finite value here. Suppose during the designing of the transformer, okay, during the designing, if size of the transformer decreases, okay, if size of the transformer decreases, so then operating frequency of the transformer will be increased, that to maintain this V by F ratio, V1 by the EMF per turns ratio constant. Okay, so see here all of you, suppose, so this is if size of the transformer decreases, okay, decreases, then operating frequency of the transformer, okay, will be increased in order to maintain, okay, this ratio constant, okay, constant here. So therefore what is the conclusion here? So during the designing of transformer, okay, designing of transformer, what will happen? So हम क्या कर रहा है, इधर साइज को डिक्रीज कर रहा है. सो अब अगर साइज को डिक्रीज करने के, अगर साइज को डिक्रीज किया तो क्या होगा, फ्रीक्वेंसी, ऑपरेटिंग फ्रीक्वेंसी विल बी इंक्रीज. सो इन ऑर्डर टू मेंटेन दिस रेशियो कांस्टेंट, सो दैट मीन्स इफ द AN is a decreases, okay, so then the operating frequency of the transformer that should be increase, okay, that should be increased. So this operating frequency that should be increased that to maintain, so this ratio constant, okay, this ratio in order to should be the increase, okay, the increase that to maintain the V1 by the F ratio constant, okay, E1 by F, the ratio constant here. Got it my point? So all of it clear here. So during the designing of the transformer, if size of the transformer decrease, okay, size को हम decrease किया था, then frequency क्या होगा? The frequency increases in order to maintain this ratio constant. So that what we conclude here. So here is a the size of the this is a therefore AN, okay, inversely proportional to frequency of the transformer. So therefore size of the transformer, okay, size of the transformer inversely proportional to the frequency of the transformers, okay, size of the transformer, the frequency of the transformers here. So that is the reason, okay, I will give some better example. See here, suppose in this case, okay, so in this case the transformer which is used in the electronic device, have you seen transformer which is used in the electronic device, any the tape record or any other electronic devices, okay, in the converters, all the UPS, transformer which is used in the electronic devices is less in size, okay, less in size as compared to electrical transformer. What is the reason? Operating frequency of the electronic system is in kilohertz, but operating frequency of the electrical side it is only 50 hertz. So that's why the transformer which is used in the electronic device must is the less in size, the in order to operate for high frequency applications, okay. And one more conclusion also there. Suppose USA made transformer and India made transformer. There are the two transformer. एक ट्रांसफॉर्मर यूएस में मैन्युफैक्चर किया था, एक ट्रांसफॉर्मर इंडिया में मैन्युफैक्चर किया था. सो दोनों में which one is a small in size, okay, like this type of question in the interviews. तो एक ट्रांसफॉर्मर है, दो ट्रांसफॉर्मर है हमारे पास. सो एक ट्रांसफॉर्मर यूएस में मैन्युफैक्चर किया था, एक ट्रांसफॉर्मर इंडिया में मैन्युफैक्चर किया था. सो दोनों में the which one is the small in size, okay, can you answer this? Okay, so which one is a small in size? What is the reason? The operating India operating frequency, electrical operating frequency the 50 hertz and ESE operating frequency the 60 hertz. For same rating, for example, same rating, the ESE made transformer is less in size as compared to India made transformer. So this is the one of the interview question. Yes, very good. Yeah, yes, Bhargav, I know you. Bhargav, yes. Okay, suppose we have a question like, so there is a one question in the this is the previous IES question. So which transformer is small in size? Okay, like this. Options are given 100 kVA, okay, the 100 kVA, the 30 hertz, okay, option B 100 kVA, okay, 40 hertz, and option C 100 kVA, okay, 50 hertz, and option D 100 kVA, the 60 hertz. Now tell me what is the correct option for this question? Which transformer is small in size? The 100 kVA 30 hertz, 100 kVA 40 hertz, 100 kVA 50 hertz, and 100 kVA 60 hertz. Yes, that's correct. ESA made transformer is small in size as compared to India made transformer for same rating. Okay, now tell me which transformer is a small in size. बताओ पहले. 100 kVA, 60 hertz. Very good. You got this answer. So 100 kVA, 60 hertz transformer is small in size as compared to other transformers. Okay. So this is the one possibility of the question. Okay. Next one. So there is the fifth observation or fifth possibility of the question. See. So that is the relation between the kVA rating of transformer, kVA rating and frequency of the transformer. Okay. So what is the relation between kVA rating and frequency of the transformer? So this relation also we can obtain by using EMF equation of the transformer. Okay, can you answer this? What is the relation between size, kVA rating and frequency of the transformer? Okay, this relation also we can obtained by using EMF equation of the transformer. See, how do we get? We know that the power rating. Okay, we know the kVA rating of transformer or the power rating of the transformer. So that is the E2 multiplied by I2. Okay. So from here we can write directly the during the designing. Okay, during the designing of transformer, during the designing. Okay, then what will happen? The kVA rating of transformer directly proportional to induced EMF here. And next one, it is also directly proportional to the induced EMF. So let us assume this is the equation 1. So now we know the E2 is equal to what? Okay, this E2 is equal to the 4.44 phi maximum Fn1. So now at constant flux and number of turns, so E2 also directly proportional to the frequency. So let us assume this is the equation 2. So from 1 and 2 equations, okay, 1 and the 2 equations, okay. So we get the kVA rating of transformer. Okay, this is the kVA rating of transformer directly proportional to the frequency of the transformer. Okay, so this is the frequency of transformer. So it is also the one more the observation or another possibility of the question from the EMF equation of transformers here. Okay, all of you clear point? kVA rating is directly proportional to frequency of the transformer. Okay, and size of the transformer is inversely proportional to frequency of the transformer. And the one more possibility of the question, so that is the sixth one. So that is a relation between the maximum flux density and this maximum flux density and the V1 by F ratio, the E1 by F ratio of transformer here. So where V1 is nothing but what? Okay, here is so where the V1 is a supply voltage, okay, supply voltage, and frequency is F is a frequency. So what is the relation between flux density and V1 by F ratio of the transformer? So this relation also we can obtain by using the EMF equation of the transformer. How do we obtain? By using EMF equation of the transformer. So we know that EMF induces in the secondary winding, in the primary winding. So that is the E1 is equal to 4.44, the B maximum, AN, the F, N1, okay, AN and F. So now during operation of the transformer, so what will happen? See, so this AN and N1 are, okay, size of the transformer and number of turns are fixed at the time of the designing, and are clear point, the size of the AN, size of the transformer and number of the turns are fixed at the time of designing and treated as a constant during operation of the transformer. So is it possible, can you change the number of turns during the operation of the transformer? It's not possible. Okay, can you change the size of the transformer while operating or under operating condition? No, it's not possible. So that these two are fixed at the time of the designing and treated as a constant during operation of the transformer. So in above equation, see, so in above equation, okay, so that is a AN and N1 are the fixed at the time of the designing, okay, at designing and treated as, okay, these are the treated as constants, okay, constants the during operation of the transformers. Okay, all of you clear point, these two are fixed at the time of the designing and treated as a constant during operation of the transformer. Suppose this is also constant and this one is also constant and here is also constant, so that you can write, so therefore the during operation of transformer, so this is a the E1 the directly proportional to product of the flux density B maximum and the frequency. So from here we can write, therefore the B maximum directly proportional to the E1 inversely proportional to frequency, where E1 is a directly proportional to applied voltage. I am not talking about equal. E1 as applied voltage increases, EMF induced in the transformer also increases. So is a directly proportional to the applied voltage. So therefore we can write the B maximum directly proportional to the V1 by F ratio here. So this condition is valid only the during operation of transformer. Okay, while operating the transformer, the B maximum directly proportional to the V1 by F ratio. So this relation is a very important in entire discussion of the transformer. If we know this relation, we can answer the many question in the losses testing, okay, in the hysteresis loss, eddy current loss, okay, in every calculation. So we have to use this relation. So it's a very, so any question comes belongs to the operating side, we have to verify whether flux density is a constant or not. So if the flux density B maximum is directly proportional to V1 by F ratio. Okay, so these are all possibility of the questions from the EMF equation of the transformers. Okay, actually one question, what is your question? Shrutika, why does frequency increases if area decrease to maintain ratio? Why to maintain ratio? Okay, that's correct. See, EMF actually in this case every time we don't know. Okay, for example, we have a transformer, okay, that is a 10 kVA, okay, 400 upon 200 volts transformers. Okay, so in this case, okay, initially, so this is the, we have to design this transformer. Our objective is the design 10 kVA 400 by 200 volts transformer. So for example here the voltage per turn is there, voltage per turn, the voltage per turn is the 2 volts, okay, this is, so this is it depends upon voltage per turn, that depends on size of the conductor, okay, this also length of the conductors. Okay, so voltage per turn is a remain same, okay, always same. Suppose in order to induce the 400 volts, so how many, okay, how many number of the turns are required? So 1 turn, okay, that generate the voltage of the 200 volts. Okay, now here is in order to get 400 volts, so how many number of the turns are required? Suppose in case of the primary side, right? So now 1 turn generate the voltage of the 2 volts and 400 volts, so how many number of the turns are required? So now this is equal to, okay, number of turns in the primary winding. So 400 okay divided by the 2, that is equal to the 200 tons are required. Okay. So now similarly in the secondary winding, okay, so this ratio is the same, voltage okay per turn, so that is equal to 2 volts, right? So now 1 ton okay generate the voltage of the 2 volts. Okay, to generate 100 volts, okay, these are 200 volts. So how many number of tons are required? So that N2 is equal to 200 divided by 2, that is equal to 100 tons. So now tell me here, is it constant or not? Suppose if it is a constant, voltage, conductor here, voltage per turn remains same from primary winding to secondary winding. So while changing the size, okay, then what will happen? We have to maintain this ratio constant. Okay, we have always, this is the basic relation. So we have to maintain V by F ratio constant from primary winding to the secondary side of the transformers. Okay. Any more question do you want to ask? Shrutika, have you got it? समझ गए आप? और कुछ सवाल है क्या आपके पास? आप कितना भी सवाल है आप तो आप पूछ सकते थे. Thank you Gopal. Voltage per turn means the एक turn by using 1 ton. Okay, एक टर्न यूज करने के बाद कितना वोल्टेज आ रहा है, ये वोल्टेज सेम होना चाहिए फ्रॉम प्राइमरी टू द सेकेंडरी साइड. Okay, thank you very much. So these are all observations or possible questions from the EMF equation. I already mentioned that derivation of EMF equation is not important, but behind that, what is the questions behind the EMF equation of the transformer? So that part is a very important for competitive exams. Okay. So now let us solve some questions here. Now read the question, all of you. The rating of primary winding of a transformer having 60 number of the turns, okay, 60 number of the turns is 250 volts, okay, 50 hertz. If cross sectional area of the core is 144 centimeters square, then okay, then the flux density in the core, option A 1.2 Tesla, 1.3 Tesla, 1.4 Tesla and 1.5 Tesla. Okay, now tell me what is the answer. All of you first read the question. Read and try to solve this question. Okay, if you get wrong answer also, there is no problem, I will make it correct. Okay, see here, what are the given data here? The given, so that is the number of tons N1 is equal to 60 number of the tons, and area R, the AN is equal to 144 centimeter square. Okay, this is 144, and supply voltage, the V1 is given, so it is the primary winding, okay, rating is given, so that means, so EMF induces the E1, so that is equal to the 250 volts, okay, it is excited with the rated voltage, and frequency F is equal to the 50 hertz. So which one we have to find? The flux density of the transformer. So that is the B maximum we have to find. So what is the value of the B maximum? So I already mentioned that. So there is a one, by using the first observations we can answer this question. So we know that, okay, E1 is equal to the 4.44, okay, B maximum ANF, okay, FN1 number of the tons. So we required flux density. Okay, remaining parameters are given in this question. So therefore here the B maximum is equal to the E1 divided by, okay, 4.44 ANFN1. Okay, this. So this B maximum is equal to, so E1 is a 250, okay, divided by 4.44, okay, net cross sectional area here. So that is a 144 into 10 to the power of minus the 4. Okay, here we have to convert into, so that is a in meter square. Okay, that is a centimeter square. So multiplied by, so now this is a frequency of 50 Hz, number of turns is 60. Okay, therefore you can get B maximum 1. So now calculate 1 point. So it is a Tesla, means it is a Webers per meter square. Webers per meter square, or it sometimes Tesla. So that's why we have to convert area into the meter square. Now calculate this value here. Okay. So answer is 1 point, the nearly equal to 1.3 Tesla. Yes, that's correct. Okay, have you clear, all of you, about this question? So next, let us solve another question. Okay, solve here. A 50 Hz 100 kVA 1200 upon 400 volt single phase transformer has flux density of 1.2 Tesla and induced EMF per turn of 30 volts. Find net cross sectional area of the transformer core. Okay, EMF per turn of, okay, this is a, the how much amount of EMF per turn, that is a given E1 by N1 is equal to 30 volts. Okay, this is the given data. So now the V1 by N1 is equal to 30 volts and maximum flux density B maximum is a 1.2 Tesla. And one more, what about the frequency? F is equal to the 50 Hz. So now let us calculate the net cross sectional area of the transformer core. So we know that the EMF per turns ratio is equal to, so E1 by N1, so that is equal to 4.44, okay, B maximum ANF. Okay, so now substitute here, the E1 by N1 is equal to 30, the 4.44 B maximum, so that is equal to 1.2 Tesla. That means area we will become the, that is a Webers per meter square. So now this is the AN. Okay, it is the directly we have taken Tesla. So that this is the meter square only. Okay. So now in this case multiplied by the frequency. Okay, frequency how much? The 50 Hz. So now therefore calculate AN is equal to the 30 divided by, okay, 4.44 1.2, okay, into 50. Okay. So now calculate this part. Okay, 30 divided by Okay, 4.44. One point two into 50, right? So that is a okay. What is the answer? 0.1126. Okay, 0.1126 26 meters square. Which 0.1126 meters square. Take up to 4 digits. So answer should be up to 4 digits. So up to the 4 digits. So that is the 0.1126 meters square. Very good. The Pratik given 0.11 meter square. Very good, very good. Okay, Shrutika also got these answers. Very good. Okay, next, solve one more question. Okay. Yes, yes, Shrutika, that's correct. Right. So now first read the question here. If 100 kVA USA made transformer is operated in India, then value of maximum permissible kVA rating of transformer will be. Option A 100 kVA, option B 83.3 kVA, option C 50 kVA, and option D can't be operated. Okay, 100 kVA USA made transformer is operated in India, then value of maximum permissible kVA rating of transformer will be. How do we answer this one? 100 kVA, 83.3, 50 kVA, and option D also can't be operated. Now, can you answer this one? So ESA made transformer means, okay, so that is the transformer, okay, is designed in the ESA. So that here the designing frequency here, okay, this is the designing frequency. So in this case, okay, it is a 60 Hz. Transformer is the designed at a frequency of, okay, 60 Hz, and it should be operated in India. So therefore operating frequency here, okay, this operating frequency, so that is the 50 Hz, okay. So to be operated, okay, this means to be operated. So this India में operate करना चाहिए. So डिजाइन क्या है यार, डिजाइन कितने फ्रीक्वेंसी में डिजाइन हुआ था, 60 Hz में हुआ था. So लेकिन 60 Hz फ्रीक्वेंसी का ट्रांसफार्मर इंडिया में 50 Hz फ्रीक्वेंसी में यूज करना चाहिए. So तभी एक क्वेश्चन आएगा हमारे पास. क्या क्वेश्चन है, ये यूज कर सकते या नहीं, okay, this type of the question. So now this option D is there. So transformer is designed at a frequency of the 60 Hz, but it should be operated at a frequency of the 50 Hz. That means, okay, in India, okay, this the in India. So now what is the question? What is the kVA rating of transformer? First we have to know whether it can be operated or not. Okay, it can be operated or not. This type of the question. So always to operate the any machine, the operating value should be less than the designing value. Okay, here is. So to operate, okay, to operate. So this operate here. So this operating value or operating the values, that should be the less than or equal to the designing values. Okay, this is the designing values. So it is operated, okay, here. So to operate any machine, okay, this the to operate. So this is the to operate any the machine or the device. So the machine or the transformer, what will happen? So here operating value must be less than or equal to the designing value. So by using this, okay, we can say that so 60 Hz transformer can be operated for 50 Hz, but we cannot operate up to the rated kVA. Okay, we can operate with the reduced rated kVA. So what we conclude here? So by using this, okay, the yes, okay, this is the 60 Hz transformer can be operated. Okay, this is the can be the operated, okay, 50 Hz, okay, 50 Hz with reduced kVA rating. So what is the relation between the kVA rating and frequency here? So we know that, okay, we know here, okay, we know the kVA rating of transformer, okay, this kVA rating the directly proportional to frequency of the transformer. So now this is the kVA rating. So in India the divided by the kVA rating, okay, in the ESE, so that is equal to, okay, this is the frequency in India divided by frequency in the ESE. So now simplify this, okay, kVA rating the in India, okay, that is the permissible kVA rating India. So that means permissible, okay, permissible the kVA rating in India, that is equal to the 100 the into 50 by 60. So that is equal to 83 3 kVA rating. So that means so ESE made transformer 100 kVA ESE made transformer is operated in India. Okay, you can operate in India the up to what value? Up to the 83.3 kVA ratings. Yes. Okay, in the interviews also sometimes we have a question, अगर 60 Hz का transformer 50 Hz में use कर सकते हैं या नहीं? So definitely you can use the 60 Hz transformer. The can be used, the designing, it is a designed at a frequency of the 60 Hz but operated at a frequency of the 50 Hz. So it is a less than the rated value, so that there is no problem. Okay, so now another question. Now can you answer this? If 100 kVA India made transformer is operated in ESE, then the value of maximum permissible kVA rating of transformer. Option A 100 kVA 83.3 kVA, option D 120 kVA and option D can't be operated. Okay, now tell me the answer. 100 kVA India made transformer is operated in India, then what is the value of maximum permissible kVA rating of transformer? So first verify what is the designing frequency here. Okay, this is the designing frequency. Transformer is designed at a frequency of, okay, 50 Hz, right? So now the to be operated, okay, to be operated at a frequency of, okay, that is the 60 Hz. Why? Because the to be operated in USA. So it is designed in India. So that's why designing frequency the 50 Hz and operating frequency the 60 Hz. So now see, verify here the operating frequency, okay, this operating frequency is greater than the, okay, designing frequency, okay, this designing frequency here. So that it can, it so therefore, so here it can't be operated, okay, for safety purpose, okay, safety purpose only, okay, it can't be operated. So it can't be operated, so for safety purpose, okay, safety purpose only. So which option is the correct here? Option D. Yes, even though if it is operated, suppose practically the 50 Hz transformer is operated above its rated value, practically what will happen? The flux density increases and thereby the here what will happen here, losses increases, temperature rise, they may chance to get the damage. That's why for safety purpose the always operating value should be less than the designing values, less than or equal to the designing value. Okay, now answer this question. If transformer is operated by keeping flux density constant and frequency is reduced to below its rated value, then flux density of the core would be. What will happen? Flux density of the core. If transformer is operated by keeping flux density constant and frequency is reduced to below its rated value, then flux density of the core would be. Option A increased, option B decreased, option C remain same, option D increased or decreased. Okay, so this question you can solve by using the one of the observation, that is during operation. First see this question, it is operated means transformer is operated. So what it means? This question belongs to operating side, okay, not about the designing side. So that's why we can write, so we know during operation of the transformer, okay, this operation of transformer, so this is a maximum flux density B maximum directly proportional to the V1 by F ratio here. So what is given? Flux density by keeping, so actually this one is a by keeping applied voltage, not the flux density. So in transformer is operated by keeping voltage constant and frequency is reduced to below its rated value, then flux density of the core. So it is a typing mistake, so just make it correct. By keeping voltage constant and frequency is reduced below its rated value. So this what will happen here? So here is a by keeping voltage constant, frequency is reduces, the flux density of the core, okay, will be increased. So therefore flux density of the core will be the increase. Okay, therefore, okay, here is a, as applied voltage V is a constant and frequency is a less than the F rated, so then what will happen here? Flux density of the core will be increased. So option A is a correct. Increases, very good. So now solve one more question. If transformer is operated by reducing voltage along with the frequency such that V by F ratio constant, then the flux density of the core would be. Option A increased, option B decreased and option C remain same, option D increased or decreased. ओके इस क्वेश्चन में क्या किया था, वोल्टेज को डिक्रीज कर रहा है, फ्रीक्वेंसी को भी डिक्रीज कर रहा है, लेकिन V बाई एफ है ना, ए रेशियो की कांस्टेंट है. सो एट दिस कंडीशन व्हाट विल हैपन इन द फ्लक्स डेंसिटी बाय रिड्यूसिंग वोल्टेज along with the frequency such that V by F ratio constant, then what is the change in the flux density of the core? The remains same. So here we know that this question also belongs to which side? The during operation of the transformer. So therefore during operation of the transformer, okay, so this V maximum directly proportional to the V1 by F ratio, right? So by reducing the voltage, okay, along with the frequency such that V by F ratio constant. So when V by F ratio constant, when the V by F ratio constant, okay, this ratio constant. So then what will happen? The B maximum also constant. So B maximum remains same. Option the C is a correct. Very good. Next, solve this question. So it is a remain same. Now this question. If applied voltage of the transformer is increased by 50% and while frequency is reduced by the 50%, then the core flux density of the core will become option A 3 times, option B 3 by 4 times, and option C 1 by 3 times, and option D remains same. Okay, now tell me the answer. Do it fast. The same. Okay, Karthik given same. Okay, is it previous question or this question? 3 times. Try yourself. Try yourself. You will get an answer. If you get a wrong answer also, there is no problem. Okay, you must try. ट्राई करना पड़ेगा आंसर के लिए. अगर गलत भी हो सकता है, अगर सही भी हो सकता है, लेकिन आप ट्राई करो. Okay, see here. So if applied voltage of the transformer is increased by the 50%, while frequency is reduced by the 50%, then core flux density will become. Okay. So this question also we can solve by using the the relation of B maximum directly proportional to the V by F ratio. So therefore you can write, okay, we know the B maximum, okay, directly proportional to V1 by F ratio. Clear my point? So from here B maximum, okay, 2 is equal to B maximum 1. The into this equation is a directly proportional, so that V12 by the V11 and multiplied by, okay, it is a inversely proportional F1 by F2. So this relation is a, you can write directly B maximum 2 by B maximum 1, it is a directly proportional V12 by V11, okay, here the V1 F1 by F21. So let assume, okay, here let the V11 is equal to V. Okay, these are some applied voltage V. So here applied voltage of the transformer increased by 50%. So increased by 50% means, okay, it is a 100%. So it is the per unit value, what will happen? The V12 will become 1.2 times of the V. Thus similarly, okay, let F is equal to, F1 is equal to the F. Okay then. So then F2 will become, okay, see here, frequency is reduced by 50%. 50% from 100% to the 50% is reduced. That means 50%. What is the per unit value here? That is the 50% divided by the this is the, so V1 to the F2 is equal to 0.5. Okay, 50% means is in the per unit value, so 0.5 F. Okay, so now we can write the this equation. Now substitute here the B maximum 2 is equal to B maximum 1. The into, okay, V12 is a 1.5 times of the V. Okay, now this F1 is equal to F and F2 is equal to 0.5. So that the B maximum 2 is equal to 3 times of the B maximum 1. Yes, option D is not correct. 3 times is the correct. Why you are getting option D? The C here. Suppose numerator and denominator both are increases by 50%, B maximum remains same. Numerator and denominator both are decreased in the same proportion, B maximum is decreased. So one is a increase, other one is a decreasing. Definitely what will happen? B maximum 2 is equal to 3 times of the B maximum 1. Yes, that's correct. So now let us solve this question. A single phase 50 Hz 400 upon 200 volts transformer has flux density of 1.2 Tesla. Am I right? When excited with a rated high voltage and frequency. So if same transformer is excited with a voltage of 300 volts at a frequency of 40 Hz, then the value of the flux density in Tesla. Flux density in Tesla. Okay. So can you answer this? A single phase 50 Hz 400 by transformer. So we have to find out the flux density of the core. So this is initially 400 upon 200 volts transformer. So excitation given to the rated high voltage side. Okay, this side is the excited. So that means supply voltage is equal to 400 volts. So now it is a 50 Hz transformer. So under this condition, B maximum 1 is equal to how much? 1.2 Tesla. Okay. If same transformer is operated at a voltage of the 300 volts and what frequency? 40 Hz frequency. So then what is the value of the B maximum values? Okay. So we are operating. This question belongs to operating side of the transformer. Okay, got it point? So a question operating side, the question which belongs to the operating side of transformer. So that we can write the during operation of the transformer. So during operation of the transformer, so what will happen? B maximum directly proportional to the V1 by F ratio. Okay. So by using this, what we conclude? B maximum 2 is equal to the B maximum 1, the V12 divided by V11 multiplied by F1 by F2 values. So now tell me what is the V12 here? So in this one is the case 2. Okay, like. So now this is the initial case 1. So V12 means, okay, B maximum 2 is equal to the B maximum 1 is a 1.2 Tesla. Okay, here V12 is equal to how much? 300. So V11 that is a 400, right? So now frequency F1 is equal to 50. So now F2 क्या F2 का क्या? The F2 value is the 40 Hz. So now simplify here the B maximum 2 you will get. कितने B maximum 2? कितना आएगा B maximum 2? बताओ पहले सॉल्व करके. 1.125. Very good. Atul Singh Rajput given 1.125. Okay. Param also got 1.125, right? So let me calculate. I will also check whether it is a correct or not. Okay, into 300. Yes, that is a 1.125 Tesla. Very good. This correct. Okay. So now solve one more question. A 200 volts 100 volts 50 Hz transformer is to be excited at 40 Hz from 100 volt side. For exciting current to be same, the applied voltage should be. For exciting current to be same, the applied voltage should be. Okay, now tell me the answer. What is the applied voltage? $80 volts. Very good. Any other answers you got? Okay, see what is the meaning of exciting current? Okay, there is a question here, exciting current. The exciting current means, okay, see here, exciting current, it is nothing but another name of the no load current. No load current of transformer. So this no load current is a, okay, this I naught. So always, okay, it is a magnetizing current plus iron loss component of current. I will discuss this question about this equation in the next classes, okay. But here given that as exciting current as the I naught constant, okay, then so what will happen? Magnetizing current will be constant, okay, right? So when magnetizing current is a constant, the flux is also constant, okay, and the flux is a constant, the B maximum is also constant, okay. So these are the, as I naught is a constant, the B maximum is a constant value. So here given the during operation, okay, this during operation of the transformer, so then what will happen? B maximum directly proportional to V1 by F ratio. So what it means? Okay, to get this B maximum. So at B maximum, whenever B maximum is constant, okay, this one is a, the when the B maximum is a constant, okay, constant, then what will happen? So V11 by F1 is equal to the V12 by F2, okay, this under this condition. So V11 by F1 and V12 is equal to F2. So initially in this question, so it is a 100 volts, 200 by 100 volts 50 Hz transformer is to be excited at 40 Hz from 100 volt side. So that means initially 100 volts, okay, 50 Hz transformer, okay, 50 Hz, and initial case from 100 voltage side, okay, this is the frequency given, okay, frequency 40 Hz. So then what about this voltage? Okay, it is the V12, okay, it is the V11, okay, it is the frequency F1 and F2 values, okay. So this is the given in this question, okay, given. So now substitute here, okay, V11 is equal to how much? That is a 100, right? The frequency 50 and that is equal to, okay. So V12 is a, we don't know, okay, we have to find out F2, where F2 kitne? So that is equal to 40, okay, now find out. So this is a V12 is equal to 80 volts. Yes, that's correct. 80 volts is a correct answer. Okay, have you got it? So now let us solve one more question. So now tell me, this question also given in IS 2014. So very important question. A single phase two winding transformer is to be designed to operate at 200 volts or 200 volts 50 Hz. Okay, 200 volts, sorry, 400 upon 200 volts 50 Hz. If the HV side is energized at a voltage of the 440 Hz, then the no load LV side voltage, okay, the no load LV side voltage of the transformer. So for example, see here, so this is a transformer, okay, see, very important, the somewhat difficult to understand this question, okay. The see here, okay, this is the primary side and I have taken the secondary, okay, this is the secondary side, okay. So now this is a EMF induces here, okay, which transformer rating is a the 400 upon 200 volt side, okay. So this is the here is a always, okay, E1, so no voltage, okay, this one is the 50, HV side is energy rise, that means, okay, this side is a energy rise at a voltage, okay, that is a 400 volts, right. So now this side is a the 400 volts, what frequency here? So that is the 400 volts and 50 hertz frequency. Okay, sorry, this is the rated value in this case. Okay, 400 volts and 50 hertz. So now this side is a, okay, the no load. No load means no current flows to the secondary winding. Okay, this is the E2 values. Okay, so now here what is the no load LV side voltage should be? Options are given: 300 volts, 250 volts, 200 volts and 150 volts. So now what is the answer? Anybody guess? So see, it is similar to, okay, by keeping voltage constant. Okay, here is a, this question is nothing but, so by keeping voltage constant, okay, voltage constant and frequency reduced below its rated value. The frequency is reduced, okay, reduced below its rated value, below its the rated value. So then what will happen here? Okay, under this condition, so what will happen? So during operation of the transformer, so during operation, B maximum directly proportional to V1 by F ratio. Okay, so by keeping voltage constant, see here, voltage constant, frequency is reduces, the maximum flux density of the core increase. So when maximum flux density is increases, the maximum flux of the transformer will be increased. So that means to increase the maximum flux density, so to increase B maximum, so this should be increases. Okay, this should be increased. So in case of the saturation region, okay, in the previous class I have mentioned that. So suppose it is a magnetizing current and this one is the flux phi here. So initially what will happen? So as a magnetizing current increases, okay, flux is also increases linearly, so up to the saturation point, and after that the flux remains same. So in order to increase the flux in the saturation region, okay, initially, so this is the saturation point, okay, and this point is a operating point. So now if it is operated other than the rated frequency, the transformer core goes into the deep saturation. Okay, this one is a, the transformer core, the shifted, this is a operating point 1. So from here, so it is a shifted to the other point, so that is the operating point 2. So in this case 400 volts and 50 hertz, and here is a 400 volts and 40 hertz. So transformer core goes into the deep saturation. So that means this operating point is shifted. So then what will happen? So which demands high magnetizing current. Okay. So this demands high magnetizing current. So due to which what will happen? The magnetizing current will be increased. But that means transformer draws very high amount of the current. The transformer that draws high current from the source. Okay, from the source, to produce the flux, to produce the same flux here. Okay, that's why. So when here is a, if it is operated less than the rated value, so there is no change in this voltage. Okay, it is always an open circuit voltage is equal to the 200 volts only. Okay, so very important question, this type. Actually most of the question comes from, so it is excited with this side, what about reduced voltage? This is a common question, but some difficult point of here. See, some logic is there in this question. So by keeping voltage constant, frequency reduces, then what will happen in the no load terminal voltage? So open circuit test. Okay, suppose we have a, I think you have done this open circuit test in your laboratory. Open circuit test conducted at rated voltage condition. So if it is operated less than the rated frequency, then what will happen? Flux density increases. So due to which what will happen? So this is the transformer draws high amount of the current from the source, and one more is a losses will be increases.
So but there is no change in the secondary terminal voltage. Okay, so this is the voltage remains same. The answer for this question is the 200 volts. Yes, by keeping voltage constant, frequency reduces below its rated value. Under open circuit condition, what will happen? No load open circuit terminal voltage remains same, but other consequences takes place in the transformer. One is a magnetizing current increase, iron loss component of current increases, iron losses increases, so efficiency here the somewhat decrease as the losses increases, efficiency, and these are the okay all. No load power factor decreases to very low value. That's why we have to operate the transformer at rated voltage and rated frequency. So all these points we will discuss in the next coming sessions, very clear. Okay, so next solve this question. Okay, solve. Two transformers of the same type using same grade of iron and conductor materials are designed to work at the same flux and current densities. Okay, same flux and current densities, but the linear dimensions of one are 2 times of the other in all respects. The ratio of kVA rating of the two transformers closely equals to option A 16, option B 8, option C 4 and option D 2. Okay, how do we answer this question? So here is a same type. Okay, one is the same type using same grade of iron and conductor material, but what is here? This is the design to work at the same flux density and current density, same flux and current densities, but the linear dimensions of one transformers are equal to the other transformers. Okay, linear dimensions means in all respects. Okay, what is the meaning of all respects? Means suppose we have a transformer core. Okay, this one is a, okay, see here. Okay, this is a okay transformer core. So what is the mean length here? Okay, this is the mean length. Okay, this one is a from ear to ear. Okay, this part, complete part, we can say that it is a mean length. Okay, what about area of the core? Okay, area means okay, this is the area. Okay, suppose if I write okay this part, okay, here I have considered, so this is the area of core, transformer core, right? So this is the mean length of the core. Okay, this side, okay, suppose it is the A side, B side, okay, the length is the A meters. Okay, for example A centimeters, B centimeters, C centimeter, and so like what about mean length here? A plus B plus C plus D, like. So now what about area here? Okay, this is the length, it is not a mean length, so length of the core and breadth of the core. Okay, like, so this one is a area of the core, okay, and breadth of the core. All of it clear? So now your question is the linear dimensions of all respect. What is the meaning of all respect means? So this length will become 2 times. Okay, not about area. Okay, this one in all respects means the smallest value. So the breadth is also will become 2 times. Okay, right? And next one, conductor's point of view. Suppose if you take the conductor, okay, this is the size. Okay, this one is a conductor. Okay, I have taken, so conductor's point of view. So what will happen is, listen. So this is the conductor here. Okay, this conductor. So it is a area, right? Okay, this area here. So this area means area is equal to the phi r square. So area cannot be double. Which one is the smallest in all respect means? So this radius will become 2 times. Okay. So this is the linear dimensions of one transformers are equal to the 2 times of other transformer in all respect. All respect means the smallest thing here. Don't take area double. The length will become double, breadth is also double. Okay, here radius will be double. Okay. So now what is the answer here? The C, I will tell you this part. Very important question. The which is gate 92. Okay, which was asked in the gate 92. So that we know that KVA rating of transformer, KVA the rating of transformer. So that is equal to E2 multiplied by I2. Okay, that is the KVA rating of transformer. So now from here the KVA rating of transformer 2 divided by the KVA rating of transformer 1. Okay, transformer 1 and this one is the transformer 2. So that is equal to the E2 multiplied by I2 divide E2 to I2 2 divided by E2 1 multiplied by I2 1. So let us assume it is a equation 1. Here 2 suffix for transformer 2. Okay. So where is the 1 suffix for the transformer 1. Okay, like. So now let us calculate the first one. So we know that here is a EMF induces in the E2 is equal to the 4.44 B maximum AN F N1, right? So this equation you can write the E2 the directly proportional to AN. So already I mentioned that in all respects means we have to take length of the core and also breadth of the core, not mean length, okay, length of the core. So therefore here the E2 2 divided by the E2 1, okay, E2 2 divided by the E2 1, then what will happen? See, okay, E2 2 divided by the E2 1 is equal to, so that is the L's, okay, L2 multiplied by B2, so that is the L1 multiplied by B1. So L2 will become the 2 times of L1, the 2 times of the B1 divided by L1 into B1. So now this will become, okay, it is equal to how much? So this will become here the 4. So therefore E2 2 is equal to the 4 times of the E2 1. Okay, let us assume it is a equation 2. Okay. So next one. So any size of the conductor. Okay, here. So we know that size of the conductor. Okay, size of conductor. The design is designed based on, okay, based on current rating of transformers. Okay, current rate. So therefore the I rating, okay, that is the I2. So directly proportional to, so which one here? The area of conductor, okay, area of the conductor. So already I mentioned that, okay, I2 is the smallest, which one here? Phi r square, the in all respect. So that means that is the I2 is a directly proportional to r square. So now here is a I2 2 divided by I2 1. So that is equal to R2 square divided by R1 square. Okay, now simplify this. So R2 square in that sense, it is a 2 times of the R1 square. So divided by R1 square. So this is equal to 4. So that I2 2 is equal to 4 times of the I2 1. So it is the equation 3. Okay, this is the equation 3 here. So now substitute here equation 1 and equation 2 in the equation, okay, this in this equation. So then what will happen? See. So from, okay, substitute the equation 2 and 3, okay, in the equation 1. Okay, then so what will happen? Okay, we get the here the KVA of transformer 2. So that 2 divided by KVA of transformer 1. So that is equal to E2 2 I2 2 divided by E2 1 I2 1. So this is the E2 is equal to 4 times of the E2 1 the into the 4 times of the I2 1. So that is equal to okay E21 into I21. So now simplify this, okay, you will get, so this is a, okay, we will get value, sorry, okay, here is, so what is the answer? Okay, it is equal to 16, right, that's correct, 16 is a correct. Yes, option A is a correct, very good. So 16 is a correct answer for this question. Okay, and this one is the last question. Okay, let us solve this question and after that we will end the session. So this is one more possibility of the question from the EMF equation of the transformer. Okay, it is also previous IES question. So this one is also previous IES question and also important for gate, this type of the question. Okay, an iron core transformer is working at a maximum flux density of 0.8 Webers per meter square, right? So its core is replaced by the silicon steel core working at maximum flux density of 1.2 Webers per meter square. So in this case, okay, 1.2 Weber. So if the total flux is remain same, is to be remain same, and what is the reduction, okay, is to be remain same, and what is the reduction in the volume of the volume expressed as a percentage of the original volume. So here is a the frequency and EMF per turns are same in both cases, okay, same in the both cases. So what is the answer for this question? Frequency and the EMF per turns are the same. Option A 33%, option B 9%, option C 22% and option C 11%. Okay, so how do we answer this question? The C here. So we know EMF per turn is equal to, okay, that is the E1 by the N1 is equal to, what will happen? So what is the relation E1 by En1 here? So that is the 4.44 B maximum ANF, okay, ANF. So given that, okay, given here, so this ratio is the constant, okay, which is given, okay, this EMF per turn also constant, and frequency and voltage per turn is remain same, okay, this is a constant, okay, so that, okay, under this condition, so what will can write under this condition? So we can write directly, see here, so that is the B maximum 1 into AN1 is equal to B maximum 2 into the AN2, okay, this is the B maximum 1 the into AN2. So now which value is given, okay, this is a, in this case, okay, silicon steel, the initially it is made with the iron core, okay, here iron core. So under this case B maximum is equal to the 0.8 Webers per meter square, okay, 0.8. So next one, it is replaced by the silicon steel core. So then what about the flux density? Okay, maximum flux density is equal to, so that is the 1.2 Webers per meter square. So it is the 1 and it is the B maximum 2. Okay. So therefore AN1, okay, see here, the B maximum 1, okay, this is the AN2 divided by AN1, so is equal to B maximum 1 divided by B maximum 2. So now what about this value? Okay, 0.8, so divided by 1.2. So now simplify this. So what is the B maximum 1? The 1 divided by B maximum 2. So that is a 0.2, 0.8 the divided by 1.2. So that is equal to 0. Okay, that is a 66. Okay, 0.66 here. So next one, and we required. So here is a percentage in the volume. So we know the volume of the core. What is the volume of the core here? So volume of transformer core. So that is equal to area of the core. Okay, area of core, transformer core. So multiplied by mean length. Okay, this is the mean length. I have already mentioned that. So complete periphery of the core, that is the mean length. So area of the core here. So now what we conclude here, this mean length is a remain same, okay, which is not mentioned anything about this mean length. So that we have to consider as a constant. So therefore volume of the transformer core, okay, is directly proportional to the area, okay, this one. So here reduction in the volume is required. So reduction in the volume means, so now it is a, we can write, so AN2, okay, this one is a, the volume of the core, so percentage, the reduction in volume, okay, in the volume. How do we get? So that is a, so how do we get this 2? So that means the V1 minus V2 divided by the V1. So it is equal to, okay, so this the V2 only, okay, V1 minus V2 and, okay, this the, sorry, percentage reduction, right? So now this is the V2 minus, okay, V1 divided by V2 into 100. The similarly AN2 minus AN1, the divided by AN2, okay, percent, upper value minus lower value divided by with respect to the higher value, reduction 1. So now this we can write, okay, multiplied by 100. So now here is a AN2 here, 1 minus AN1 divided by AN2. So into 100, so this is equal to the 1 minus the 0.66, so multiplied by 100. So that is equal to 33.3%. Like this we have to answer this question. So that, have we got it? What is the answer for this question? That is a 33%, actually 33.3%. Very good. Salman, you got the answer. And Param also got the answer, 33.3%. Like, so these are all possible questions from the EMF equation of the transformer. So how do we derive the EMF equation? What are the observations from the EMF equation? And some questions, problems based on the EMF equations of transformers. Okay. Any more doubt? समझ गए आप? कुछ सवाल है आपके पास? कुछ भी सवाल है तो आप पूछ सकते थे मुझे, मैं बता दूंगा आपको अच्छे सा. आई विल एक्सप्लेन वेरी क्लियर. Okay, is that clear everyone? Have you got it? Do you have any more questions about this topic? I think you don't have any more questions. I have explained very clear everything. Okay. Okay. Yogesh Chaudhary, what are you asking? Timing? No. Actually, so to get percentage reduction is equal to, okay, percentage reduction, that is the difference of this, okay, difference divided by higher value, okay, higher value. So which one is a higher here? See, this AN2 is a more as compared to AN1, okay. So this is a percent. Suppose percentage increment is asking, that is the difference, okay, divided by lower value, that is a multiplied by 100. Percentage reduction is the difference of this divided by higher value. So which is the higher value? AN2 is a more here. In this case, AN2 is a greater than the AN1. That's why we have taken the denominator is I. percentage reduction, percentage increment, the difference divided by higher value into 100. Percentage increment is the difference, the lower value multiplied by 100. We required percentage decrement, that's why we have taken difference of these and higher value divided by higher value. Yes, have you got it? Suppose compare here B maximum 1 and B maximum 2 also. Okay, very good. So initial case it is the B maximum 1 is equal to, so what is the initial value here? Okay, this one is the initially 0.8. So now B maximum 2 is equal to 1.2. So with respect to this also we can answer. Okay, here is a inversely proportional. So one is a increase and decreases. Okay, AN2 divided by AN1 is equal to the here AN1. So now it is a, so this one is, so higher value means it is a V1 only, right? That's correct. Difference in the higher value. So difference you can take. So higher value, that is a AN1, AN2 divided by AN1. Okay, that's correct. Have you got it now? Difference, which one is a higher here? So this is a, okay, AN1 is a high. AN1 is greater than the AN2. So that's correct. The V1 you can take difference. Okay, and it is the V1 and AN1. So that's why the difference in the means, okay, it is a, the V1 is a higher, that's why we can take AN1 minus AN2. So that is a 1 minus, okay, AN2 divided by AN1. Okay, got it? Otherwise I will tell you here also, see. The percentage, the reduction in the volume is equal to the V1 minus V2 divided by V1 multiplied by 100, right? So now here is a, so this is the A1 minus A2 divided by A1 into 100. So now it is a 1 minus AN2 divided by AN1, so into 100. So now it is equal to, so what is the value of AN2 by AN1? So 1 minus 0.66 into 100. So that it is equal to 33.3. Okay, so difference divided by higher value. So instead of writing I have written here 2. So that is the correct. The reason behind the taking this formula, finding the volume. So what is the here is a, we required percentage reduction in the volume only. Okay, volume. So what is the relation between? But we know the relation. Okay, this is a given that EMF per turns ratio constant and frequency also constant. Okay, which is here V1 by the N1 is equal to the 4.44 B maximum AN and F. So after getting this is a constant means, so we can write, okay, it is a, the B maximum AN is a some constant. Okay, that's why we can write. So here what is the relation? We got a relation in terms of the area. So what is the relation between area and volume? Volume of the core is equal to area core multiplied by mean length. So mean length means just exactly periphery of the core. So this mean length is the periphery of the core. So that's, this core is the remain same. Only So periphery remains same, but the length and breadth of the core will be the change. So that area will be the change. So that's why we have written as a percentage reduction in the volume directly proportional to area of the core. Okay. So we have taken from this relation directly. Yes. Thank you all. Thank you very much. We'll meet tomorrow. And happy Holi to all. Okay. I wish you happy Holi in advance. And thank you very much. Okay guys, thank you very much. We will meet tomorrow at same time. And if you have any more question, you can ask. And if you have any doubts about any question, please feel free to contact with me while by using my Telegram group. The Telegram group is provided in the link. Okay, thank you. So you can ask any question also, any type of the question about this topic, and practice one more time, and first read the concept very clear, and after that think about the question formation in that concept. So that is the what are the possible question from this concept, and after that practice previous year questions of GATE, previous years of the questions of the ESE from 91 to till date. So if you have any more questions, you can ask. So timing, my class timing daily 11 AM. Yogesh, class timing is a daily 11 AM. Every day, the morning 11 AM. There is a problem with link. Okay, just wait. I will. Okay, tomorrow I will provide the link. You can join in the link. No issue. If you have any other groups of GATE Academy, I'm sharing the link every day. You can join by using that link. Okay, thank you all. Thank you very much. Bye. Take care.